Recording. Let's revise what we discussed yesterday first. Then we will proceed with today's objectives. So, can any one of you tell me what we revised, what we did yesterday?
We should start, na, Kantigita?
Hello,
Ma'am, students are still in lobby. Just give me 2 minutes.
hello, hello. Am I audible to you guys? Hello, am I audible?
Yes, you're audible.
Yeah. So, can any one of you tell me what we discussed yesterday? Okay, fine. Okay, so yesterday, what we did is first, we learn how to use this optimetrics function, right? So if we have assigned any variable to a particular function, so yesterday we have seen how to sweep current as well as how to change material of your object. Like for transformer, we have discussed how to change material for core, right? And along with that, we have uh, we have learned how to calculate losses for windings as a total loss for winding
First,
as
we're doing
well as
the
individual
session
losses
is
for
name,
each
the
winding,
subject
right?
induction. Even during your induction, we have to heard.
Hello,
Next, during your knowledge,
hello.
you must be aware the session is on mentoring program, right? Which happens at SSB in the third year and the fourth year. Are you aware of this? You remember seeing this in our presentation when you got inducted by.
Hello. Okay, now it's fine. So if you don't have any questions or if you don't want to ask any doubt, please mute yourself. Okay. Okay. So today, what we will be discussing is we will be discussing how to calculate core loss. Then how to draw geometry for inductor. Actually, before I was not planning to like teach inductor, but now because you guys are so familiar with transformer, I thought we should like introduce one more geometry. So today, whatever we discuss will be in terms of inductor. Is that fine?
Yes, ma'am. Yes.
Yeah. So let me share my screen first. First, we will like learn some basic things about inductor. Then we will start with our geometry. Okay. Uh, just give me a minute. So till yesterday, no one has any doubt. Huh? Whatever we have discussed till yesterday, does any one of you have any doubt in that?
No,
Mm,
ma'am.
no. Okay, fine. Just give me a minute. I'm joining by my iPad.
Yeah.
So the first thing is for inductor, we need to have air gap in the core. So why we need this air gap in transformer? It's not like usually we avoid air gap, but in inductor we need air gap. So why we need this air gap? First we will discuss that. Then we will proceed with our geometry. Okay. So
Okay, ma'am.
if this is the current carrying conductor, then what do you guys know Ampere's law?
Yes, ma'am.
What is Ampere's law? So by Ampere's law, the magnetic field produced by the electric current is directly proportional to the intensity of electric current and constant of permeability. Okay. So if we write that in terms of equation, it will be B dl equals to mu I, right? Right. If it is just air, then we will write here mu naught. But for now, we will just write here mu. Five. So uh, in inductor, if we don't want our core to saturate, we have to increase our saturation current. Okay. So how core saturation takes place and why we should avoid it? Uh, this is like your assignment for tomorrow. Please search this. Okay. Saturation of core. Fine. It's fine. Okay. So if for saturation current, what see, let's assume our inductor has we are dealing with multiple number of turns. So let's assume that n is the number of turns. So this equation will become right. So through this we can calculate saturation current. So it will be like this. So I'm not discussing this in detail. You can read about it later. But for now, I'm just like telling you the importance of air gap because in inductor we will have that air gap in core. Okay, so it saturation then mu. So we are writing through this. We are writing the equation of saturation current. Okay, into L upon N. Fine. So if we just rearrange this, this is the area of core. Now we are assuming that we have core, right? First we were assuming that it is air, but now we are just like we are assuming that we have core. So here I'm just writing AC and AC, which is the area of core, because I want to rearrange it in terms of reluctance. Okay. This is just simple mathematics. You don't need to worry about this. So if we just rearrange it, this part, just if we just keep n here, then this part becomes reluctance. N AC L upon mu. Okay. So this is rho L by A, right? This part. So I saturation will become R. So we have replaced it with reluctance. Okay. So if we just have core, so reluctance will be RC. But if we introduce an air gap in it, example, this is our inductor. Okay. I know it will be difficult for you to understand at this point, but if you will read it in detail, you will understand all this. Okay. For now, we just have core. So R what R will become? It will just become RC. But now if we introduce here some air gap, what it will become? RC plus RG, right? This reluctance will become, this is RC plus RG, right? So now we know that R is equals to rho mu by AC, right? And RG, RC, LG. Ultimately, if we just write RG upon RC, it will be like LG upon LC upon into mu naught upon mu C. This is air gap. So here, what will come? Permeability of air. That's why I have write mu naught. What is permeability of air? One. Permeability of air is one, like free space. Then LC, we have mu C. Yesterday, I have told you it's a like the permeability of core is high, very high. Okay. So we are assuming it to be 2000 times mu naught. Okay. So RG upon, and we are assuming, see, this is the length of core and this is just the length of air gap. So we are just assuming that our length of air gap is 1 centimeter in terms of our like example of LC is 100 1 mm, sorry. If LC is 100 mm, then LG is just 1 mm of it. So ultimately what we will get, LG upon RG upon RC will be equals to 20, right? So with just 1 mm of air gap, we can increase our saturation by 20 times. If we just replace it here with just 1 mm of air gap, we can increase our saturation current by 20 times. So our core will not get saturated easily. Understood? with just like introducing this air gap. That's why inductor air gap is necessary, okay, to prevent saturation of core. This part you understood? But and also actually I think this equations parts are very boring, so I'll just tell you the importance of air gap in inductor, because like you can read this somewhere else also, but here because we are just dealing with Ansys part, so we will concentrate more on it. So first is saturation of core can be given, and second is uh, our inductor is a energy storage device, right? So our energy density also increases. So like is equals to half Li square. So if you just replace it with this uh, I by this and L by Ni upon sorry, N phi upon I, so you will also see that your energy density also increases for inductor. But with transformer, what happens is this is your air gap. So leakage will takes place, right? So it might it will affect your inductance value. But because inductor is an energy storage device, it is advantageous for us. But transformer is a energy transfer device. So there we cannot afford leakage. Whatever we are primary flux gets linked with the secondary flux. So we don't want any leakage in between, right? So in transformer, most of the time, like this air gap is avoided. You understood this? I know it's a bit difficult to understand, but just read it after this class. You will understand all this. Okay? Read it in details. You will understand it. Fine. Should we proceed with our geometry?
Yes, ma'am.
Yeah. So this is the geometry that we will be uh, simulating today. I know I have not shared this geometry with you, so you can just plot it with me, or I'll share it after this class. Okay? So uh, whatever manual I have given you, their experiment, I think 5 or 6 is this, right? So I'll replace it with inductor. First, I was thinking that we will do everything with respect to transformer, but because we already got familiar with 2D transformer, that's why I thought that now we will also like we can also draw we can also analyze inductor geometry. So that's why in your manual also and replace this. Okay, fine. Let's start. Now I'll not tell you this. You already know this now, right? How to draw the geometry you guys know now, right? Please speak up. So your X size is Y size is 42. Here it will become minus 21. Your So both your x and y are 42 mm. So you just have to position it at -21, -21. Okay. This you understand, right? Because we have already discussed this. Similarly, we will now draw the windows. This your x size is 28.6. Your y size is 8.65. Here it's 28.6. And this one is 8.65. So its positions on that is 14.8. Here is 6.1. Six five. Okay, we will duplicate it and just mirror it. Okay. Then what we will do is we will first select our name, then subtract. I have not said. Okay. Till this, you know already how to do this, right? Now we will introduce some air gap in the core. So it's of 2.2 mm air gap. I'm rushing here because you already know how to draw this geometry. Do you guys want me to repeat this again or it's fine?
No, ma'am.
Right. Okay. So now we will introduce 0.2 air gap here. Let's draw one rectangular first, then we can just adjust it later. As 0.2, your x size will be 21. Your x size will be to calculate x, just a minute. Twelve point. Yes. This is uh, check its length. Yes. Just a minute. Okay, so actually I got little bit confused with this air gap thing because in my drawing also I have not written all the parameters. So this is 6.25 x sizes, y is 0 0.2, so this is of 0.2 mm. Okay, and then its position -21 we have decided according to this. This is like this is -21 in x direction, and in y direction because we want to place it in the center, it's 0.1. You understood this? I'll give you this geometry. You try it yourself. You'll understand this. Okay. We'll duplicate this also. Just keep here 0, 0, 0. If it is not in the correct position, just keep here 0, 0. Look up. Sorry, I know I'm struggling today because I have not planned on introducing inductor to rise. So I just today I've decided to draw this geometry. So I also don't have like perfect dimensions and all of this. Okay, but we'll be fine. Okay. Hmm. Fine. So we were I was facing some difficulty with duplicate mirror option. That's why I've decided to use move. Like I've told you, na, we can just copy paste that item and can use move, right? So that's what I did because in duplicate mirror, actually it should have come with this axis, but I don't know what was the issue. But it's fine. We can use multiple options because we have it. So what we will do is we will subtract this also with from our code because we want to introduce air gap, right? First, this. Okay. Now you can see that we have air gap in our code. Understand this? So now we have four turns of winding. You know, in inductor we don't have primary and secondary. We just have one winding, right? Just two terminal winding, right? So we will draw here four turn winding. So this size is 28.6. Y size is 0.3. X size, sorry. Then position is 0.5. From here will be 14.3. And I've done something like
Ma'am, increase the exposition, I think so, ma'am.
What I did wrong is, I have just calculated it from the window. I forgot this space. I forgot for X size. And also, what you said? Sorry, I didn't get it. What?
Increase the exposition, ma'am. Actually, you are placing it near to the y-axis, no, ma'am. If you increase the exposition, it will be. That's
X was not the issue. Sorry, X was the issue because I have not calculated this and just have was doing it from here, like from window. Okay.
yes, ma'am.
Okay. Sorry for this. Okay. Again. Something other than it's all super correct. What windows I have taken? Uh, or
Ma'am, 14.3, ma'am. 14.8 is it.
nine. That was 19.6 here.
Yes, ma'am. Yes, ma'am.
29.6 here. Okay. So it should be 29.6. By mistake, I have written 28.6 here. Okay. Now it's correct. Okay. Fine. Okay. First move, if the distance between them is 0.5. Okay. Then for this, again move. So this is on 5.51. Okay. And then binding was left. This one. Okay. Now we have 3. So we will just duplicate it on the other side. Okay. So we are done with our geometry. What is the next step? Hello. What is the
Yes,
next
ma'am.
step? What is the next step? Boundaries, right? Okay, let's zoom out this. Uh, Actually, I was a bit unprepared for this geometry. That's why I was struggling. But yeah, fine. Done with this. So let's move on now. So the next step is we will introduce a boundary. Okay. What we will do for boundary? Edge
Select the edges.
Right. And we will assign balloon boundary, right?
Yes, ma'am.
Okay, fine. Let's change it to transparency. You guys remember this, right? Color we will keep as it is. We will just change the transparency. Yeah. Then let's assign material. So for now, we will um, for winding, we will assign copper material. This you all already know how to do it. That's why I'm just like I'm not telling you guys because I've already explained this to you, right? This is better for me. Okay, that's correct. After fit all, I was like confused if this space is uniform or not. But yes, it's uniform. Then our bindings are done. Then this is your core, right? So in yesterday I told you that we will learn how to assign a new uh, material, right? So for core, in the previous class, we directly used to use ferrite core, right? But today we will just assign a new material to it. So what I have done is I have uh, taken, so I have decided which core I want to use. And then what we have to do is we have to take out its data sheet. So the core we will be using today, its name is 3C85. Okay. So the first thing that we need to do is go to it, take out its data sheet from Google. So this is the data sheet for 3C85, right? Now for like you have to listen to this carefully because it's like uh not a bit actually, it's very confusing thing. Okay. Go to this triangle, go to edit, then click on add material. Okay. first assign its variable. Sorry, first let me assign material to this, then we will add it. Right. Something wrong. I'm forgetting something. Yes, sorry. Okay. Sorry. Go to add material, then in relative permeability, go to non-linear, then here a VH curve will come. Here you have to put values of B and H. Okay. So how the values of B and H you will get? You will get it from data sheet. Okay. So there it is for you can see a BH curve in the data sheet. Whatever material you selected, it's first you have to take out its data sheet. There a BH curve will be given. Okay. It will be given for 25 degrees Celsius and 100 degrees Celsius. I'm uh, putting values for 100 degrees Celsius. So you can you can take any H value and corresponding to it, you can put any a B value. Means what is the corresponding B value? For example, 25. So what is the corresponding B value? You can put. So like that, you have to put like uh 5 to 10 values or more. Like you have to form a table for it. So like select your own value. It's not necessary that step size should be same or not, but like select a set of H values and corresponding B values, then you can put. Okay. So from this curve only, uh, I'll be putting values here. This table, the table that I am writing here, I have I've taken these values from this BH curve only. This you are understanding? Okay. Actually, like a table like this will appear. Okay, let me show you. Yeah. You have to write table in this form. Okay. So this values we are putting in our own geometry. Fine. One thing also you can do is you can form an Excel and it just can import data. That is also an also other way to do this. Okay. So you got the same table that we have seen here, right? Because our values is in millitesla, we will just change it this to millitesla. Sorry, it's 250. Okay. Then actually to calculate your core value, you need to know some values, right? So composition is, so let's first see this. Oh, I'll share my screen from iPad. Just wait. Huh? For core loss model, you also have to put, for calculation of core loss, you will need K, X, and Y. I'll tell you where to put this. Okay. So for calculation of this value also, you will need your data sheet. Okay. So let's, how core loss is calculated. You guys know how core loss is calculated? It's calculated using Steinmetz equation. So what is that equation? It's PV, which is core loss equals to K F alpha P beta. This is some constant. This is frequency. This is flux density, and these are also constant. Okay. Now, how to find this constant? First, I'll just tell you the direct formula for this. It's log of PV2 upon PV1 upon log of F2 upon F1 for constant B. Okay. And beta is equals to log of V2 upon V1 for constant frequency. And K you can calculate just by putting the values of alpha, beta at some frequency, some B. So it will be like this. K equals to PV okay. My screen is visible, right? So now how you will get this value? you will get this value again from the data sheet. Now, just search it here only, maybe it will be then easy for you. Can you see this graph? Yeah. This is core loss versus flux density graph. Okay. So how you can get it? Example, if you have chose your frequency to be in the range, how this 100 kilohertz to 200 kilohertz, then at a fixed B, you have to see, example, I'm choosing 1000. Okay. It is in millitesla. Example, I'm choosing 100, sorry. So for these, you have to first see what is the value of for 100 kilohertz, what is the value of PV for 100 kilohertz, and same, what is the value of PV for 200 kilohertz. Then you have to substitute it in this PV1 upon PV2, and your frequency will be 200 upon 100 for fix B. You understand this? Is it confusing? Hello? Should I explain it again?
Yes, ma'am.
You understand or it's confusing? Like, what is yes, ma'am? You want me to repeat again or you understood it?
Yes, ma'am. We understood it, ma'am.
Okay. Similarly, beta, you have to calculate in the similar way. So what you will do is, you will now keep your frequency fixed. So example, I'll just see for the 100 kilohertz. Okay. I think my stylus is not working here. Okay, fine. So just for 100 kilohertz, you will see at different B what is PV. Just for you are seeing this 100 kilohertz graph example. This is just an example. So you will see at different B what is the value of PV. Then again you will substitute it here. Okay, PV2 upon PV1, B2 upon B1 at F constant. Understood? So by doing this, like you can, it's not like everyone will get the same value because they can choose any B, any F. Okay, but it is more or less same. You guys understood this? Guys understood, or should I just repeat it?
Repeat it, ma'am.
Okay, fine. So, uh, let me just open it in good notes, then and maybe I'll able to explain it better. This is your V versus PV graph, right? So what is alpha? It's log PV2 upon PV1 upon log F2 upon F1 at constant P, right? So from here, see, I'll choose one constant P. For example, I have choose first, let me choose my frequency for, so for F2 upon F1, I have chosen 200 kilohertz and 100 kilohertz. Now I just want, I have to see these two graphs. Okay. Then I'll choose my B constant B. So I'm choosing 100. So this is 100, right? Then I'll just draw this. This is just an example. You can choose any B value, okay? Corresponding to them, you will get some PV value, right? Right? This will be your PV2 and this will be your PV1. Now you understood? So put this value PV2 and PV1 here, and then F2 as 200, F1 as 100, and then you will get your alpha value. By substituting this, you can get your alpha value. You understood this now? Is it clear?
Yes, ma'am.
Okay. Then similarly for beta, its log PV2 upon PV1 log B2 upon B1 for F constant. Okay. So now you will choose only one graph from here. Example, I have choose 50 kilohertz means any like 100 kilohertz. What it means for what you are designing, you should choose that. Okay. So example, now I have choose 100 kilohertz. So for 100 kilohertz, now I'll just see this. Now I'll just see 100 kilohertz graph. Okay. And then for, let's assume my first B1 is 100, no, 100, and my second B1 is something here. Okay. So corresponding to this, you will again find your PV2 and PV1 values. And then substitute it here and calculate beta. Now you understood? So from here you will get alpha and beta, and K you can just substitute it and find K. Alpha beta you can substitute for some PV, like you can take this point only. So PV, here you want fixed PV. What is the frequency? 100 kilohertz. This will be PV. And what will be B? 100 millitesla. You understood this? How to calculate alpha, beta, and K? It's still confusing. Just please respond like. Hello. You guys understood it or not? Is it too much for you?
Yes, ma'am. A
And
little confusing, ma'am.
yeah, I know at this stage it is too much for you guys how to add material and all, because I don't know like data sheet and all you have read before. Uh, you've seen data sheets and all. You are in third year, right?
No, ma'am. No, ma'am. It's first time.
No, what in which year of engineering you are?
Yes, ma'am.
Third year, right?
Uh, Currently in third year, ma'am. Third year semester one.
Okay.
Semester one. Yes, ma'am.
Okay. So what you want me to do. Should I skip this part? Like, I'm not understanding. It will be very confusing actually. Okay, fine. I'll just tell you then how, like, this is the way to do it, and I don't know any simpler way to explain you things actually, because you have to use datasheet if you want to put your own material. Okay. Okay, fine. Okay.
Okay, ma'am.
One thing we can do is, for now, let's just put this values. Tomorrow we will start this fresh, and like in the first half an hour, I will again try to explain this to you, like little bit slowly. Fine? Is that fine? Okay. I just shared. I know these things are a little bit confusing for you now, but it's fine. I'll just tell you how to put values and all. Okay. And tomorrow again, we will repeat this in the first half an hour. Okay.
Okay, ma'am.
Yeah. So we were here, right? So then in loss model, you have to select power ferrite. Here, Cm is the value of K, which is 12, which we calculated from datasheet only. X is 1.3, which is alpha, and Y is 2.55, okay, which is beta. This all we calculated. I just, I have not shared my screen. Sorry. Okay. So here, uh, it was none before. We will replace this core loss model by power ferrite. Then here, Cm, X, and Y will come. In Cm, you have to put the value of K from your formula that I just told you how to calculate it. Okay. In X, you have to put 1.3, and in Y, you have to put 2.55. Okay. Then just, okay, and assign it to your core. Understood? Okay. For now, don't take tension of this. Just just put the values and assign a new material to your core. Tomorrow, I'll again try to explain it to you. Okay. I'll just search for some simpler way to make you understand things. Okay. Fine. Then what is left? Our boundary is done. Material assignment is done. Then what is left is you have to give some current to the windings, right? So here we don't have primary and secondary winding. We just have what we call this is what we call as like positive. We have this is inductor. So just we have one winding, two terminals, positive and negative. So this windings we will give positive current and this negative. I told you how we decide the direction positive and negative, right? Right? You guys remember this or not? At least excitation, you know, na how to give. Hello. Hello.
Yes,
Is it
ma'am.
too much for you today? Should we stop here? Should we continue it tomorrow? Please tell me because you guys are not responding. It's fine. We can like continue it tomorrow. I'll just explain it to you again.
Okay, ma'am.
No, what you want, tell me.
Ma'am, let
Because
us continue tomorrow.
okay. So what I'll do is send you the geometry today. You simulate that on your Ansys, and from tomorrow we will start fresh. Okay.
Okay, ma'am.
Okay. So I think for today it is too much for you guys. I should have taken care of that. Okay, fine. It's fine. We are ahead of our time, so it's okay. Because anyways, today this is like experiment 6, and today is just day 4. So we are anyways ahead of our time, so it's fine. We will discuss this tomorrow again in detail. But what you guys have to do is you have to plot this geometry and do everything with me, right? I'll send you this. What's I'll send you the geometry today because I don't think you have this. So I'll send it to you. Just plot it and be ready with it tomorrow. We will discuss this freshly. Okay? Everything,
Okay, ma'am.
just the geometry part we will skip. We will start with the material assignment, excitation, means transient analysis, everything we will do tomorrow. Because if I'll explain things to you today, I think you will be like very confused because you guys are not responding at all. So I think it's too much for you for today, I guess. Right? So let's today we just learn why we need air gap in inductor and how we can simulate our inductor geometry. It's like transformer only, but just additional air gap we have to put, right? Then tomorrow we will do its transient analysis. We will learn. We will see how core loss is calculated. We will see how uh, new material is given, and also what is left? Yeah, then like we will tomorrow we will not give like means we will not give a simple value like single value of current like we used to give before 10 8 to today tomorrow we will give sinusoidal current and we'll do its transient analysis. Okay, so that also I'll cover tomorrow. But please whatever I'll send you today, please simulate that geometry in your Ansys so that tomorrow you will not get confused. We will just start fresh with material assignment and we will move forward. Okay?
Okay, ma'am.
Yeah. Thank you. Rakesh, sir? Hello?
Ma'am, actually, Rakesh sir is not participating today.
Okay. Okay.
Thank you,
Just
ma'am. Thank you.
yeah. Let him know that because like We will continue this class tomorrow. I'll anyways message him. It's fine. I'll message him. Okay.
Okay, ma'am.
Yeah, but please, whatever Vamshi, I'll do one thing. I'll send you the geometry. Please circulate it in your WhatsApp too. Okay.
Okay, ma'am.
And ask
Okay, ma'am.
everyone to just keep the simulation.
Yes,
Draw the
ma'am.
geometry. Okay.
Yes, ma'am.
Tomorrow,
Okay, ma'am.
I'll try to means slower so that you will understand the things.
Yeah.
Okay.
Okay, ma'am.
Actually, because we have plotted the geometry and all, it has become too much for you guys. I understand. So it's fine. It's fine. You are in your just third year and you are learning Ansys. It's a big thing. I just learned it in like first year of PhD. So it's fine.